kick off this lecture.
Yes. Okay,
So,
we will have Pekka again today, and Pekka will talk about nickel, flash smelting of nickel. And Pekka, time is yours.
Thank you, Imam. Good afternoon, ladies and gentlemen in Asia and Pacific area, and good morning for those who are attending this lecture from European sites, wherever you are. So my topic today is nickel matte smelting, and I will give you some ideas about the processing of nickel from sulfidic ores. Nickel as such is much smaller metal than copper, about 10% only from the total copper production. So its annual production is around 2.5 million metric tons. And today most of nickel is used for stainless steel making, and we will see in the future how this demand and use by application will change when electric cars will be needing a lot of more nickel than before, and also the need will be substantial in the important side metal byproduct of nickel production, which is cobalt. So it is still much smaller metal than nickel, and it will be the big problem within 10 years in our electrifying society. So we have two sources of nickel in the world. So two types, or different types of ores available. So the large amount of nickel is available in various laterites, which are oxidation products of nickel sulfides, and they are available mostly in tropical environments, and their nickel content concentration is low, typically from 1 to 3% only, and they cannot be beneficiated. They cannot be enriched by mechanical or flotation methods at all. So they are, as such, they are either smelted or treated by hydromet methods. So the product of these lateritic nickel ores is typically ferronickel, but some smelters are also producing pure nickel and pure nickel products by sulfidizing the reduction products in laterite smelting. Smaller part of nickel is available in magmatic sulfide deposits, which are very unevenly distributed around the world. So we have even continents which don't have nickel ores, and then we have large nickel producers in certain areas. So nickel sulfide ores are typically smelted to matte, and then this matte is produced to pure cathode nickel or some other nickel product, nickel briquettes or nickel powder in hydrometallurgical refineries. And as you see from this bit old figure, so the production has been increasing all the time, and also the demand certainly, and that means that as I said, the annual production of today is around 2.5 million tons of nickel. So the nickel processing is rather complex, even if the smelting step is very close to copper matte smelting, and the complexity of the overall process chain, which is shown here on the left hand side, comes from a couple of specific issues which are typical to nickel sulfide ores. So we have along with these nickel sulfide minerals, which typically are pentlandite, we have chalcopyrite in the ore, which is copper carrier, and those copper minerals are extracted in the mines and concentrators because of their economic value. So all smelters are treating along with nickel also significant amounts of copper. So it's a question of nickel copper separation into hydrometallurgical refining circuits. It's not so much about the pyrometallurgy, but then nickel ores are important sources of many minority elements and trace elements. Typically, most of cobalt comes from in the world comes from nickel ores, and most of platinum group metals are also coming from nickel production. So these are very important sources of revenues for the smelters, and therefore the recoveries of these minority metals are also important, and they are probably more important in nickel smelting than in copper smelting. So this means that both in the smelting side and also in the refinery, so hydrometallurgical processing of the matte, we need a lot of skills in order to get good metal recoveries and not to waste these trace elements into the landfills of slag and other residues possible forming in the processing. So these nickel resources in the world, they are distributed very unevenly, and also the share of sulfide ores is much less than laterite ores. So we have these laterites in most cases in tropical climates, and sulfides are, as I said, they are magmatic ores. So they are located independent of the climate wherever the ore has been formed. But the share of laterites really is much larger than that of sulfides from all nickel resources. But the primary production, the production from ores and concentrates, it is and has been up to now primarily using sulfide ores. So this pie chart, so it's a couple of years old. It shows that almost 60% of total nickel production came from sulfide ores and minerals, and about 40% are based on laterite smelting and hydromet operations, which you will be hearing later. So, as I said, nickel matte smelting chemically and in terms of technical operations, they are close relatives to copper matte smelting, because in a similar way as chalcopyrite, the main mineral in copper pyrometallurgy, the pentlandite is containing a lot of iron, so approximately the same atomic fraction of iron as there is nickel, and that means that the smelting operation as such is dealing with the elimination of that sulfidic iron and sulfur, and in that sense, so these operations in the copper smelting and nickel smelting are relatively similar. Also, the skills needed to treat nickel sulfide concentrates is rather close to that of copper sulfide concentrate treatment, but you must be aware, for example, looking at Ellingham diagram of nickel and iron, copper, and probably cobalt sulfides and oxides. So nickel is less noble than copper and cobalt as well. So cobalt is even closer to iron, and that means that excessive oxidation of nickel can happen in smelting conditions if the process is not controlled properly. One feature which is not seen in typical copper concentrates is the gang of high MgO, high magnesium oxide concentrations, which is typical to nickel ores. And this is the major challenge in many nickel smelting operations. I will discuss this detail a bit more in slides which are coming soon. So we have probably two technologies used in nickel matte smelting today, so that flash melting technology has gained area in recent, say, 50 years. So most nickel sulfide matte is produced by flash melting. We have another flash melting technology which is not used widely, but it was developed particularly for making nickel mattes. It's the Canadian Inco flash melting, which is different from Outotec or Outokumpu or Metso Outotec today flash melting technology, but the chemistries are pretty much the same, and phenomena in the furnace, except this high reaction shaft, which is in the Outotec flash melting furnace. So the other technologies used in this area are electric furnace smelting of nickel sulfide calcine, so partially roasted nickel sulfide concentrate, which was used probably only in one smelter in the world. Whether that is still operating in Sudbury, I'm not pretty sure, but that was in the past a major producer of nickel. But all the other smelters in the world are using flash melting, Outotec flash melting technology, except those who are treating these special nickel concentrates, which contain very high platinum group metals concentrations. So they are typically in South Africa, those deposits, and they don't have enough sulfides to sustain flash melting heat balance. So such ores and concentrates are typically treated by methods which are allowing external energy to be used in the smelting, probably more flexibly than in the flash melting furnace. So such technologies typically today are electric furnace and these TSL bath smelting processes, which are used in South Africa. Actually, these concentrates are not called nickel concentrates, even if nickel is the main product and copper is the second largest volume product. They are called platinum concentrates because of the huge concentrations of platinum group metals. Probably ores having more than 10 grams per ton, platinum group metals even more. So these nickel flash melting furnaces are similar and probably identical with copper flash melting furnaces, and they have reaction shaft, settler, and uptake for the off gas. So smelting reactions, heat generation, use of oxygen, it is taking place within the reaction shaft where dry concentrate with fluxes is fed, and formation of matte and slag is taking place in the settler below the reaction shaft, where these particles, fine particles, after this partial oxidation, settle and start forming slag and matte in a similar way as in copper smelting processes carried out with flash melting technology. So dimensions, temperatures, and gas flows are similar to corresponding copper smelting furnaces, but as I told you yesterday, those oxidation degrees of the matte, they are adjusted in the same way in both sides, copper and nickel smelting, based on the oxidation degree of the matte which is targeted, and the metal grades, fractions of sulfide materials in the feed mixture by this oxygen coefficient variable explained yesterday. So everything is in good balance, and as I said yesterday, for copper flash melting, the key operation parameter in flash melting is the heat balance. If that is not okay, so the furnace is not operating properly, and after that we can adjust oxidation degree of the matte and other things in a wide range of operational points. So when these fine dry concentrates are added or fed into the reaction shaft using the concentrate burner, they start heating up and reacting with the surrounding oxygen in the process gas. So at some point, when the particles are heating up, their ignition point is reached, and they start burning very quickly, within tens of milliseconds. A particle typically of the size of, say, 40 microns in diameter or something like that, on the average, is combusted from sulfidic state to fully oxidic state, depending on how oxygen is available in its surroundings. And here we have some laboratory scale experiments on the sulfur removal during the flight in a flash melting process. These are from laboratory scale drop tube experiments showing that this pyrite concentrate is the most eager one to react, and it reaches complete desulfurization when in this duration of the experiment, which was few seconds, 1 to 2 seconds. When the gas temperature initially before the oxidation was 700, and chalcopyrite and a nickel concentrate are less reactive, and from a literature source, this nickel concentrate was even less reactive, so it lost it was oxidized, it lost its sulfur slower than the other nickel concentrate, and also much slower than pyrite concentrate. So this is the kind of reason why we generate a lot of heat in the reaction shaft, and why the reactions, due to the very fine dry feed material, are very quick, and they complete their reactions with the surrounding gas really in a time span of what is available in the reaction shaft of typically 2.5–3 seconds as a total flight time. So some words about the mats in nickel matte smelting. So because sulfidic nickel concentrates contain chalcopyrite, the nickel matte will contain also copper. So nickel sulfide smelting produces a matte, which is a homogeneous liquid phase dissolving nickel and these other sulfide favoring elements, major elements like copper, cobalt, iron. And then this molten sulfide is also very good solvent for various trace elements, typically silver and gold, as in copper smelting, but also platinum group metals, platinum, palladium, rhodium, osmium, iridium. I will talk about their behavior in smelting a bit later also. So what kind of molten phases these industrial nickel sulfide mats are? They are not chemically mixtures of the main sulfides, but they are sulfur deficient, referred to these sulfides of theirs in a similar way as in copper making. So there is less sulfur than what we would have if we just add this iron sulfide, iron monosulfide, copper sulfide, and hazelwoodite, so nickel sulfide together. And this is a consequence of the smelting operation and the formation of a gas atmosphere, which contains sulfur, oxygen, and mostly sulfur dioxide. So this gas atmosphere, which is present when this matte is formed, it is burning away, so to say, more sulfur than these pure sulfides have, which actually generates more energy in the smelting vessel. So this is the general characterization of nickel sulfide mats. And they also, in the same way as copper mats, dissolve small amounts of, or small fractions of oxygen, depending on the iron content, because the solubility of oxygen comes from the iron sulfur oxygen corner of the nickel sulfide mat. So iron is actually the carrier of oxygen in the molten mat, and it comes out when this nickel mat is solidified as magnetite precipitates from that sulfidic matrix. Here I have plotted, calculated a phase diagram, so liquidus isotherms of a system containing copper, iron, nickel, and 3% cobalt, which probably is a typical nickel to cobalt ratio in sulfidic ores. And this metal matrix has been defined to contain 21 weight% sulfur in all locations of this Gibbs triangle. And you can probably see, it's rather small, but you can probably see that these isotherm temperatures are pretty low in certain areas of the mat. So at low iron concentrations, over quite a wide range of copper to nickel ratios, we have liquidus temperatures which are below 600 C, and probably this 3D diagram shows it in a better way. So when we have this is the liquidus surface in a 3D presentation for a bit different mat system now containing 20 weight% sulfur, and you can see that lowest temperatures here are really below 900 K, which is 600, about 600 degrees centigrade, and this is a nuisance in industrial nickel making, because our smelting takes place where the slag is molten, and depending on MgO concentration of the concentrations of the slag, the smelting takes place at 1350, 1400, 1425 C. So now we have below that slag layer, we have mat which has a melting point of 600 C, meaning that it's at least 600 degrees lower than the slag. So that means that even at temperatures which are found in the refractory brick lining of the furnace vessel, nickel matte is molten, and this is causing rather harmful and actually dangerous leakages in nickel smelting furnaces, leakages which may come through the brick joints or some loose kind of construction details through the corners of the settler or some other part of the furnace. And it is dangerous in such a sense that if you look at the temperature where these mats are fluid, where they are molten, so they are below that limit where your eye sees that it's hot. Solid part and liquid parts start glowing when their temperatures are close to 800, and this may be close to 600, and what you see coming from the furnace is a black liquid stream, which actually is so hot that you can burn yourself seriously if you don't realize that it is actually molten matte, not water from some broken pipe or something like that. So these matte leakages are actually rather painful problem, and you must be aware of such phenomena if you are working in a nickel matte smelting company. So what happens in the reaction shaft when pentlandite and other sulfide minerals are oxidizing? So we are forming matte, but along with that matte formation, we also lose chemically some nickel, some copper, and probably most of cobalt into the slag, and these are chemical reactions which cause those chemical dissolutions, and in the same way, many trace elements dissolve in the slag as oxides. We have verified that silver, gold, platinum, palladium, their dissolution into the slag is dependent on the prevailing oxygen activity of the system. So if this is true, and we have verified it in many ways and in several separate studies, that proves that the oxidation is the mechanism for the minority components to dissolve from sulfide matte into the smelting slag. And this is scientifically important because many years we believed that the dissolution, chemical dissolution, for example, of platinum is not possible because of the very low stability of platinum oxide. But for example, palladium oxide is relatively stable as a pure substance, and it behaves in a similar way as platinum in nickel and copper smelting systems, as I will be telling you a bit more later. So when these valuable metals are dissolving in the slag, we also see similar kind of oxidation of iron from divalent iron 2+ into the trivalent iron 3+ oxide in the slag. So this is important for the slag cleaning operations, in particularly in nickel matte smelting conditions, because there we are recovering much more of these dissolved elements and metals in the slag than in copper pyrometallurgical copper slag cleaning. So as in the case of copper matte smelting, the real art of smelting nickel matte is in the fluxing, in that operation where we try to keep, and we must keep, the fluidity of the slag on a suitable level. So iron oxides, as mentioned yesterday, forming during the oxidation steps of the nickel and copper sulfides, they are solid at the smelting temperatures. Here is part of the iron oxygen phase diagram, and this is the molten domain of liquid iron oxide. So it is close to iron saturation. It is formed at, say, 1370 or something like that C. But when we go to higher oxygen activities, to the domain of magnetite as the primary phase, so we are then here. This is magnetite phase field, pure solid magnetite, and here we have hematite, and this is the primary phase field of magnetite in the iron oxygen phase diagram, which is then expanded into 3D triangle or system when silica is added and temperatures are also lowered to allow, for example, copper smelting at 1300, as described yesterday. So in addition to these slag fluidity problems in pure system, in pure iron oxygen silica system, so we have now additional components in our smelting system, and the most influential are the MgO, magnesium oxide, concentration of the feed mixture, and also to some degree, but not very strongly, the forming copper to nickel ratio of the matte So this is influencing the chemistry of the matte very much. It is diluting nickel more than what nickel concentration would be in a binary nickel sulfur system, and that is why we don't use in scientific literature, we don't use the same type of variable as used in copper smelting for describing the degree of oxidation of the system. So this matte grade is not a good variable in nickel smelting if we look only at the concentration of nickel in the matte. So many older scientific papers on nickel smelting only talk about the concentration of nickel in the matte, but they don't report even, but they don't pay attention to copper, which is actually a diluting component in nickel mattes, and thus decreases its activity when copper is present at high concentrations. High concentrations here mean certain large volume concentrates available from Canada and Russia, where copper to nickel weight ratio is typically 1:2 or 1:3. So we have out of the total nickel amount, we have half of that, or one third of that copper present in our matte, which is a major diluter, at least from the compositional point of view, and thus those nickel mattes containing a lot of copper and those mattes containing very little of copper, they may behave in very different ways, and this is a systematic change in the thermochemistry and thermodynamics of the matte. So I prefer to use ion concentration of the matte as a measure for the degree of oxidation, and in all of those papers who have been published from other university dealing with nickel smelting, we have tried to avoid this nickel concentration alone to be the measure of the oxidation degree, because it's not. It's the true ion concentration in the furnace matte, which is actually shows the degree of oxidation in the system. I have a couple of times mentioned about the major nuisance in nickel smelting, which is the gangue in many nickel sulfide nickel ores, and this gangue is typically, but not always, some sort of magnesium silicate talc or something like that, which is very strong modifier of iron silicate slag. and that means that it changes the phase relations at low concentrations in the slag, and that is why nickel matte smelting is carried out at slightly higher or even more than 100 degrees C higher temperatures than copper matte smelting. And how this slag modifying is seen in the phase diagram of typical iron silicate slag. So I have here iron oxide silica, so FeO, Fe2O3, SiO2 phase diagram at 1350 degrees C, and this black line shows the molten domain of iron silicate slags from spinel, so magnetite saturation to iron saturation, and from silica saturation down to FeO, so wustite saturation. So if we put 2% magnesium oxide into this slag, so our molten slag domain is slightly, but not very much, decreased. It is also shifted a bit towards higher silica levels. That means that our silica saturation is slightly increased by MgO addition of 2 weight%. And then this green line is showing the same liquid phase domain when MgO concentration in the slag is 5%. So it is only 5%, which is rather low concentration, but it shows also that this kind of nose is penetrating gradually and splitting into two this molten phase domain. So the available slag concentrations, which are fully fluid, they are much less. They actually, when magnesia concentration of the slag would be increased by 2% up to 7%, and further on to 10%. So we would see here two separate domains of molten slag, one for low silica concentrations and one for higher. And this is a serious problem because today we have smelters in the world which are facing the MgO concentration in their outcoming slag of close to 10%. And that means that slag has a high viscosity. It may be a two-phase slag with some solids in it, and this means a longer tapping time, and the operation is actually limited by slag tapping in worst cases. So in some cases you don't be able to empty the furnace because the tapping periods are extended so much due to this high MgO in the slag that that something must be done. And this something is actually to some degree it has been solved some 25 years ago in a way I will show you a bit later. So what is making this trouble in the slag? It is solid olivine compound which is magnesium silicate of this type. So it has two magnesium or ions and divalent magnesium and ions and one silica as a compound. It has a melting point of nearly 1900, and that comes out when MgO concentration of the slag is increasing beyond probably 6 to 7 weight percent. It has the feature that it increases because it is solidified in the slag. There is two phases, molten and solid phase, that will increase the viscosity of the slag. So this is a serious problem, and in a even more serious way, it may form solid floating kind of covers on top of the slag layer, where it is almost impossible to remove by heating up the slag only. So it also generates accretions, buildups on the inner walls of the furnace. So the effective furnace volume is decreasing, and that means that you must tap your slag more often from the furnace, and also matte, and this is also a feature which is decreasing your furnace productivity. So what has been done for this problem from chemical point of view or from fluxing point of view? So there has been a discussion about whether we can modify the slag properties by adding something in as a flux into the slag, and there are not too good alternatives for modifying these slags with high MgO. There are possibilities, but I don't know whether smelters are really using these modifiers in normal practices, probably as a last kind of possibility in running the furnace if it is otherwise impossible. As I mentioned, both copper mats and nickel mats are very good solvents for many precious metals and platinum group metals, and we have been measuring those distributions in equilibrium conditions, and here the thermodynamic property, which can be measured directly in laboratory, is the distribution coefficient of a certain minority component. So here it is the defined as weight percent of that minority metal in matte divided by its weight percent in slag, and this is a parameter which can be basically calculated if we know all the individual properties of this metal Me in the slag and in the matte, but we don't know those with a reasonable accuracy, and that is why we measure these ratios directly in laboratory conditions. And because this is a value without any scaling factor, so these distribution coefficients are valid in laboratory, but they are also valid in large-scale furnaces. So we can utilize these measured experimental distribution coefficients in estimating where our precious metals or platinum group metals go during the smelting, and then conclude what is the next step in our kind of process development, what should be done in the processing side. And here we have gold and platinum distribution coefficients experimentally defined for copper and nickel mats containing some iron, in order to get these values on the same scale in a way. And we see that for example, platinum distribution in the nickel matte slag system has a distribution coefficient of more than 10,000 and almost 100,000, and in copper matte systems it is between 1,000 and 10,000. So that means that the chemical dissolution of platinum is almost negligible in slag when we are in equilibrium conditions. If we see higher concentrations of platinum in our slags, we can conclude that it is coming from the dispersion of matte. It's not chemically dissolved platinum, but it exists as matte droplets in the slag. So what should we do? The real kind of challenge is to lower the dispersion of matte and improve the settling of this matte dispersion from the slag before discarding it. So we have also measured these distribution coefficients as a function of, like in the previous slide, as a function of ion concentration, but also as a function of kind of type of slag fluxing. And here the interest was focused on what does the magnesia do in the systems, and how do these distribution coefficients behave in matte slag systems when magnesia concentration is changing. So this is a 3D plot, and it shows clearly how at low MgO concentrations in the slag, the distribution coefficients are of the order of 2000 or something. But and at the same time, when iron concentration in the matte is 11-12 weight%. But then when we increase or our MgO concentration in the slag, or it is increased, so we are gathering more gold in the matte, and if we go further down in the iron concentration of the matte, so this is further increasing the distributions of gold. So we have here from 20 to 40 or 50,000 the distribution coefficient. So from chemical point of view and from the point of view of recoveries, it is of advantage to have some magnesia in the slag. So it is pushing these precious metals from the slag. But from operational point of view, we have too much MgO there. So we are in operational problems. So I said earlier that this problem of high MgO concentrates has been at least partly solved in the recent years. I meant a new nickel smelting technology, which I will tell within a couple of minutes. So the traditional nickel flash smelting process and smelter is pretty similar to traditional copper matte smelting process. So we have concentrate mixing and preparation, drying, feed regulation and concentrate burners, flash melting furnace, and then big gas drain for off gases and treatment of flue dusts. So this nickel matte is tapped and transferred by ladles into converters, which are of the similar type as in copper matte converting, and these converters are blowing iron down to probably 2% or 1.5%, and the product is called high-grade matte, which is typically today granulated, but some 10-15 years ago they were also cooled slowly in order to generate metal precipitates in the matte, and those metal precipitates collected a lot of these platinum group metals, so they were separated from the hydromet nickel refining circuit by that means. what happens with the matte, with the slag coming from the flash melting furnace? It will be cleaned in a electric furnace together with that slag coming from this Pearce-Smith converting step, and as a result of that slag cleaning, we have discard slag, which in some countries, including Finland, is actually used for other purposes. It is not banned by authorities because it's much containing much less impurities than copper slags. And the second product of slag cleaning is electric furnace matte, which is fed back into the converting step. And the headache here is that we have internal slag circulation here. We are oxidizing some components in Pearce-Smith converting, then we are reducing them back to the matte, which is fed into converters, and they're oxidized back into slag, and that is reduced. So this is a ever-going circulation of material which loses most of the trace elements which are transferred to slag in oxidizing conditions and reduced to matte in slightly more reducing conditions. So this is not good for cobalt recoveries, and something was improved here. In addition, that a new process for nickel smelting was kind of invented or developed in Finland in 1990s, where also high MgO concentrates could be smelted, and this kind of internal slag circulation was not anymore present. So here we have this old-fashioned traditional nickel smelter where Pearce-Smith converters are feeding slag to the electric furnace, and the electric furnace matte is fed back into converting step. And what we did and started up 1995 in Harjavalta was this kind of flow sheet. So we have the similar flash melting furnace as here, and then electric furnace. And this setup generates two different mattes. It generates high-grade matte in one step in the flash melting furnace, which is sent to refinery. And that means that we are oxidizing more nickel, more iron, more sulfur in the flash melting furnace than in the traditional flow sheet. And then the slag, which is now high nickel, high cobalt, and its volume is much more than in the traditional flow sheet. It is purified, it is cleaned in a separate electric furnace, and it proved that this slag cleaning actually is rather fast. When we started up this new smelter 27 years ago, we used the same electric furnace as before, and still it could be cleaning the slag much better than previously, partly because of absence of these internal circulations. So we doubled the recoveries of cobalt in this new flow sheet, and the nickel recovery was not worse than in the previous flow sheet. So there are two mats, as I said. First one going directly to the refinery, low iron, high nickel, high copper mat with some 20% of sulfur, and then this electric furnace mat, which is typically containing 40% of iron, but it is leachable, it is granulated in tapping, and it is sent as such to the refinery. So that means that there are no major problems in hydrometallurgical refining, even if a new leaching step was installed in the refinery for treating this electric furnace mat. So in terms of minority metal recoveries, this major improvement in the nickel mat smelting was very, very good. What happened with the slag in general? So when we look at melting temperature of typical kind of traditional slags coming from conventional flash melting process. So with high MgO concentrations, those melting temperatures may be up to 1500, which is much too high to this furnace design. And when we oxidized iron further in the flash melting furnace and adjusted silica concentration of the forming slag, so we were generating much more slag, and its melting point was much lower, so from 1420 to 1440, so a decrease of some 60 up to 80 degrees centigrade. So this is meaning that because of the increased slag volume, we can dissolve our MgO concentrations in the slag are lower, and thus we can take higher MgO concentrates in our smelting system without jeopardizing this slag fluidity. And that has been actually the more significant improvement in smelting when considering the future of nickel sulfide smelting. So what kind of process this slag cleaning is in nickel smelting? It is relatively strong reduction process in an electric furnace, where we control the ferric oxide concentration or the magnetite concentration of the slag to be tapped. And that means that we are using some reductant, here carbon, which is today the standard reductant in nickel smelters. In future, probably it will be hydrogen or biomethane, so biologically generated methane gas, which is non-fossil fuel, like hydrogen and reductant. So we are reducing first iron 3 to iron 2, so ferric to ferrous. Once ferric oxide is low enough, copper oxide starts to reduce and form metal. And after that, nickel oxide in the slag starts to generate nickel into that copper alloy. And further on the next phase, cobalt at the last of in the row will dissolve into the electric furnace bottom metal, or as smelters typically call them, electric furnace matte. And this is taking place simultaneously with the reduction of iron, and that is why the iron concentration of this electric furnace matte is high, in order to ensure high recovery for cobalt and nickel as well. So this is going according to the thermodynamic properties of these oxides and elements in the slag, and this is what you can see when the reduction process, slag cleaning process is taking progress. Some smelters add sulfur into the bottom metal, into the electric furnace matte, in order to avoid any solidification of the matte, because when this iron concentration increases very much, up to 50% or so, and in cases copper concentration in the bottom metal and in the raw materials is low, so we may end up in systems where we have a mushy solid iron nickel alloy in contact with the molten bottom metal or EF matte. And this is avoided by injecting from above nickel concentrate or some other sulfide concentrate into the interface of slag and matte. And that is why the matte is also brittle, and in cases one needs smaller particle sizes in the refining. It may be even possible to mill for increasing hydromet reactions. This operation mode of nickel slag cleaning is different from what we do in copper slag cleaning. Same kind of furnace is typically used there, but these reduction reactions are not as strong as in nickel slag cleaning. The reason is that otherwise in nickel smelting we are losing most of these elements in the slag if we don't carry out the slag cleaning with a high intensity. In slag cleaning of copper slags, electric furnaces are typically only settling furnaces, and they don't have so much reductant or not at all reductant, so that the function of this electric heating is only to keep the bath molten and allow its tapping when the settling operation is done. So if we compare this chemical process of slag cleaning in nickel industry, so it is a must. We can't recover nickel, cobalt, probably copper, yes, but not nickel and cobalt from nickel smelting slags with the typical process step mentioned by Long Gong Sha, done in copper smelting. So it is milling and flotation, and this milling and flotation actually is kind of possible in copper industry only because of this kind of reaction which takes place during slag cooling. When milling and or grinding and froth flotation is carried out in copper industry, it is in many cases as a routine nowadays carried out in such a way that the slag is first cooled down in big ladles, 30 to 50 tons of molten slag. And during this cooling step, which takes 2 days or 3, slag is gradually solidified, and there takes place this kind of reaction between chemically dissolved copper oxide, ferrous oxide in the slag, which generate magnetite dispersion. You can see that magnetite dispersion in micrographs taken from polished sections of copper slags. They are the fine dendritic magnetite dispersion which is seen there, and this reaction, in addition to generating magnetite, it also generates very fine copper dispersion in the slag, and those copper droplets are typically finer than 1 micrometer. So you can distinguish them from the polished sections, because these mud droplets which are there already before the solidification, the unsettled mud droplets, they are much bigger, 10, 20, 30 microns in diameter, and they can be recovered by milling and flotation, and due to this fundamental reaction which has driving force at the solidification temperature of the slag, so most, if not all, copper is depleted from the silicate, and the residual copper in these fine dispersions is actually the kind of residual copper concentration of the discard slag. So in in copper slag cleaning, we have typically in flotation tailings less than 0.3%. In industrial operations, less than 0.3% copper left in the tails, and it is mostly formed out of these very fine droplets which are dispersed into the matrix of the slag. What also this ladle cooling does for the slag is that it's not as difficult to crush anymore and grind. It is brittle and it has large grains which are fractured easily. So the milling after the slow cooling is not as energy intensive as it is for the slags which are fast cooled after tapping. I think this was what I had in mind now, and I think it would be now time for number of questions and comments, even arguments against or in favor. So please.
Okay. Okay, guys, now it's time for questions and or arguing about what Pekka presenting. Okay, guys, please raise your hand and you can ask the questions. Don't be shy. In the beginning, always like this. Okay, guys. So
you can also use the chat.
Yes, you can also use the chat as usual. So maybe as for information, Pekka, we also in Indonesia we producing also nickel mud, but it is from nickel oxide or laterite ore.
Yeah, I know.
Because it is laterite ore, we need electric furnace, and because there is no sulfur in the ore, we add sulfur. It's funny. So we add sulfur after from kiln, after calcination process, we add sulfur, and then we smelt in electric furnace the calcine also with sulfur added.
Yeah, it's this Inco process.
Yes, yeah, Inco process producing nickel mud from nickel oxide. Okay, guys.
Yes, I had one friend there in the plant some 20 years ago, but I don't know where he is now.
Okay. Okay, question? We have 20 minutes left. Okay, guys, don't be shy. Okay? Active student like Danes or Nabil or Hausan or maybe from other university. Please. Just raise your hand and then okay, in the chat. Very long. Maybe they are typing, Pekka, so it's take long time.
All right, let's see.
Okay, Muzoli Zaki, I will give you chocolate. A lot of chocolate.
You need an extra suitcase to return to Indonesia.
Yes.
Full of chocolate.
Yes. Good. Yeah.
Okay. So the question is about
the MGO.
Yeah. What is your opinion of if CO2 is injected into slag, the olivine will turn into iron or magnesium carbonate? Yeah, those carbonates are so unstable that they decompose below 1000. So you can't generate magnesium carbonate at 1400 or 1500. So it is not possible, but using some other kind of how to say ingredient to vaporize magnesium, what might be possible, but I don't think such a process has ever been tested, not even in lab scale. Yes,
Pekka, the idea is like because we emit CO2 from the metallurgical plant, and it is possible if we use kind of slag or tailing from metallurgical industry to capture CO2.
Yeah, yes,
To become carbonate
yes,
as a carbonate compound, and it will be stored somewhere in the soil because carbonate compound will be stable at low temperature. That's maybe the idea of Musolizaki.
Yes, I can understand that, and actually I was involved in a project in Aalto University some probably 5 years ago, where these environmental guys in another department, they had a pilot and have still a pilot plant when they treated steel making slags with such a process as a cold slag. So solidified slag, which was first it was dissolved in ammonium chloride or something, some neutral solvent which was able to dissolve slag, steel making slag, and then this lime which was present in the slag, it was used for capturing CO2. But these slags are not containing lot of lime, and magnesia content is only less than 10%. So yeah, it would be a nice idea, but in this case the solutions that would be very costly, because you would be receiving only 10% of your magnesium carbonate. The original idea was to upgrade this calcium carbonate, because it was precipitated from water, from a solution, to precipitate as a fine, very fine powder, to be used as filler material in paper making. And then it would have been rather expensive product, which would cover the cost of this kind of treatment.
Treatment. Because it is expensive, we dissolve first the slag with ammonium, and then we put CO2 injection to form calcium carbonate. So it's very costly, I think. So Pekka, this is also the issue, because it's now my question. We in Indonesia got a challenge, and from maybe government, that they asked me to apply for grant, and the topic is about reducing CO2 emission for metallurgical industry. kind of and at the time we are thinking, because in nickel slag we have a lot of magnesium, and magnesium can react with CO2 producing magnesium carbonate in some way, like you say, maybe we dissolve cold slag with kind of ammonia and then injecting, but it may be costly. And what is the, do you think the best way to reducing CO2 from, again, Pekka, we are processing nickel laterite.
Yes, yes, and
We
that
are
is,
we are using carbon
yeah,
as
yeah,
reductant. That's the
yeah.
problem. So what is, do you think, what is the best way?
Well, there you have much more magnesia in the slag. It is
Yes.
almost saturated with magnesia. So using that kind of material for this kind of recycling process, so it would be worthwhile checking. So it is a
Hmm.
simple slag because it doesn't contain any iron, and it contains mostly of silica and MgO only.
Yes. Yes.
So in that sense,
Iron oxide is fat as iron is small, but mostly magnesia and silica.
yeah, it's
Yes.
metallic iron if there is any iron left. So yes,
Yes.
this kind of raw material could be tested in that pilot, but it is still operating. So if and the cost of the the leachant or the ammonium chloride, it may not be very high because it is circulating. So it is recovered in the that step where calcium oxide or magnesium oxide is carbonated. So then the ammonium chloride is fed back into the leaching stage and so
Yes.
on. So I know the professor quite well, and he's actually I have been mentoring him
Oh,
some
okay.
years ago. So he's good friend of mine. So if I
Yeah.
could
We
I could
are, yeah.
send
This
an
September
email.
we are like, yes, we are asked to apply grant for that, because this is it is like our responsibility, because we have a lot of nickel industry in there, and they are emitting CO2, and we must think about that. And in other hand, we have rich magnesia slag. So maybe that's a good idea. Maybe I will contact you, Pekka, later about this, and maybe we want to involve you also in this project.
Yes, and then you have
Yes.
a silica there
Yeah.
as a byproduct of this kind of carbonization step,
Yes.
and you could use that silica for copper making or whatever
Yes.
flux you
Yes.
need. So it
Yeah,
could be
that's
also
cool. That's cool.
it could be also used kind of useful byproduct in a sense that it's relatively pure
Yes.
silica.
Okay, that's cool. Yeah, thanks, Pekka. Okay, guys, any more questions? We have 10 minutes. Thank you, Musolizaki. That's nice question. Uh, Other question, guys? Please raise your hand and just ask. Because today is like very specific thing. I still remember when Pekka talk about sustainability, that we time is not enough. This is kind of very specific. Okay, guys, we still have time, 10 minutes. So please ask questions. Because this is the last day of Pekka. Tomorrow we have another. Tomorrow we will use Zoom, so don't forget. And I think everyone already been sent the link.
I haven't received yet.
Okay, Danes, you should email all lecture and students.
I will
Okay.
send my today's
Yes.
and yesterday's lecture today to to you. So you will get the PDF handouts.
Okay, guys, I count until 10. We have 10 minutes. Please, if you have question or concern, you can ask. I wait until 11:51. Yes. Don't be shy. You can type in the text also.
Yeah, use chat.
Yeah, use chat. Use shy. Okay, guys. If not, then thank you very much, Pekka, and see you on November in Bandung. So you guys who take the IVC, you will see Pekka again in pyrometallurgical class and thermodynamic class. So you will see Pekka physically in November. We will invite Pekka to go there. Okay, Pekka, thank you very much and see you again.
Thanks.
Bye-bye.
Bye-bye.
Yes, bye-bye.